In this theorem, we give a nice simple way of estimating the error on an alternating series. And to remind you, the error is what we're calling the error is the remainder term Rn. So it's the absolute value of the sum of the series minus the partial sums, and in this case you can imagine it's just the sort of tail end of the series. Alright, so starting with the an plus 1 and so on. So for an alternating series, it could look something like this maybe. So the theorem is very simple. It says that if I have an alternating series that satisfies those two conditions of the alternating series test, that the terms are decreasing and eventually go to 0, then the remainder Rn is simply less than or equal to Bn plus 1. So to kind of picture it here, we can imagine that Sn, right, would be adding up the first n terms of the series. And then the actual value S here would be somewhere out here perhaps. So if we look at how the values of Sn progress, so here, going out to the nth term, we know that n plus 1 would give me us, say I added Bn plus 1 here, would give me Sn plus 1 up here. And so we can see here that would have to go past S, and then we know that the sequence will kind of narrow down towards S, the sequence of partial sums. So we can see just from the picture that if it satisfies those two conditions, that here the error, Rn, would be the difference there. And then here, this would be Bn plus 1 would be the difference there. So of course Bn plus 1 is going to be bigger than Rn. So let's demonstrate this here with a simple example. Find the sum of the series -1 to the n over n factorial, correct to 3 decimal places. And first let's just quickly verify that it's decreasing. 1 over n plus 1 factorial is certainly less than 1 over n factorial. So it satisfies that first condition. And then the second condition, that the limit as n goes to infinity of 1 over n factorial certainly going to go to 0, since n factorial goes to infinity. So this is going to go to 0. Now let's figure out how many terms of the series do we need to sum in order for it to be correct to 3 decimal places. So here, let me just sort of write out a few terms here to figure out how many terms we're going to need in order to get the sum within our desired error. So when they say 3 decimal places here, what we're really looking for is Rn to be less than 0.005. Oh, 3 decimals. So actually one more 0 there. Okay. So as long as Rn is less than this, then we know that the error will not affect the first 3 decimal places, since we've got 3 zeros in that first 3 decimal places. And then the 5 guarantees that it won't push it above or below that 3rd decimal place. So now we can start summing up the terms of the series. Here I'll just actually start writing out the terms. So we had 1 for the first term, that's 1 over 0 factorial, 1 over, or minus 1 for the next term, minus 1 over 1 factorial, plus 1 over 2 factorial, minus 1 over 3 factorial, plus 1 over 4 factorial, minus 1 over 5 factorial, and so on. Here I'm just going to write out a few more terms, and then we'll think about how that theorem might be useful here. So when I just look at these last 2 terms, in fact, here, let me just look at these values here. So this term here, if I evaluate it in my calculator, is about 0.00138. And then this term here is about 0.000198. Now, which of these terms is the first term to go below this desired error that we wanted here? Well, I noticed that here 1 over 7 factorial is the first one to go below that desired error. So we're going to treat that like our bn plus 1. So as long as the here the 7th term goes below that desired error, we know that the sum of the first 6 terms that come before it will be accurate within that desired error. So so here what that shows us is that R6 here, which is the sum minus S6, is less than or equal to B7. We showed here was about 0.00019884, which is less than that desired error that we wanted, 0.0005. So this shows that here we just need to sum up the first 6 terms of the series to be guaranteed that our error is within that desired 3 decimal places. So in other words, here the partial sum that we get from just the first 6 terms will be enough to say that our sum is accurate within the first 3 decimal places. Okay, so here we just need to add up from here to here to get S6. And if we do that, let's see what we get. So plugging in those first values into my calculator, I get something close to about 0.368. Here I'm just writing out the first 3 decimal places since we know that's going to be the desired accuracy there, so we know at least those first 3 decimal places are accurate here.